All right, last mandatory video of the school year. So, there's a third part of the trilogy. Hopefully, it's more like Return of the King than Matrix Revolutions or Godfather 3. Or, yeah, I'll say it Return of the Jedi or Revenge of the Sith. Like, I don't know. Revenge of the Sith, I guess, is the best one out of its trilogy. But Return of the Jedi was not the best movie out of its trilogy. Yeah. So, today we're going to talk about identifying sum and difference identities as well as half-angle identities in order to solve trig equations. So let's get started. For the first example, we have sine of x cosine of x plus cosine of 2x sine of x equals 1. When you are trying to solve trig equations, you want the inputs of the trig functions to be the same. So we have a 2x, we have an x, we have a 2x, we have an x. Now, you guys could use double angle identities here, but you're going to have to do a lot of work to simplify it. So rather than going down that road, I can just look at my sum and difference identities and notice that this is a sine of x plus y kind of looking thing. I remember Sinbad and Cosette, so Sinbad's with Cosette, Cosette's friend is with Sinbad's friend. So I know I could rewrite this as sine of 2x plus x should equal 1. It fits the structure for the identity that I know, and I'm choosing to condense it rather than to expand it in this instance. And I condense it because now this question is just, all right, when is sine of 3x going to equal 1? Which is really trying to get me to think about when sine of u would equal 1 if I let 3x equal u. So I know sine of u is equal to 1 when u is pi over 2 plus 2n pi. That's a general solution. Yeah, because sine is only equal to 1 in one location between 0 and 2 pi, and it's there. However, I'm not trying to solve for u, I'm trying to solve for x. So that means that 3x should equal pi over 2 plus 2n pi, meaning x should equal pi over 6 plus 2n pi. Ooh, look at that terrible writing. 2n pi divided by 3. That's pretty much all they wrote. Yeah. If you would have been using the double angle identities, which again you can, there's a lot of simplifying that goes on there because you're multiplying the double angle identities by a cosine of x and sine of x respectively. So you have to multiply, then you have to combine like terms, then you probably have to do another substitution, and then you have to worry about the fact that it's equaling 1 and not 0. Nah, pass. All right. So when you do these, try to find a structure for that fits a sum and difference identity if possible. And then it's really easy stuff to work with. So for the next one, we have sine of x is equal to sine of x divided by 2. Okay. So, like I said before, the goal of these problems is to make sure that the inputs are the same. I can't, like, if I wanted to, I could try to rewrite sine of x, but there's so many ways I could do it. I could use the sum and difference identity. I could try to force a double angle identity, or I can just focus on rewriting the right half. It's sine of x divided by 2, so I could use a half angle identity. And if I do so, I end up with sine of x equals plus or minus 1 minus cosine of x divided by 2. And I do this because now I have the exact same inputs. They're both just x's, no longer x divided by 2. So now I just have to manipulate this in a way that's more helpful. And I have algebra at my disposal, so using algebra, I can do whatever I want as long as I do it equally to both sides. And my first order of business is to get rid of that square root. So I square both sides. So then that tells me that sine squared of x should equal 1 minus cosine of x divided by 2. Okay, so I got the radical out, but now I have this. I don't like the... All right. So I'm going to multiply both sides by 2 just to no longer work with fractions. So I have 2 sine squared of x should equal 1 minus cosine of x. If I wanted to, I could try to use a cofunction identity to turn cosine into a sine, but the issue is that then it changes my input, so I'm not going to do that. I can take the sine squared and rewrite it in terms of cosine if I use a Pythagorean identity. So we have 2 times 1 minus cosine squared should equal 1 minus cosine of x. There's a big brain way to do this, and then there's I'm not gonna overthink this and just do what I know. So I'll show you big brain later, after I do it the regular way. So this turns into 2 minus 2 cosine squared of x minus 1 plus cosine of x equals 0. I distributed the 2 on the left side, and I moved everything from the right side over to the left side, so I get it to equal 0. Combining like terms, we end up with negative 2 cosine squared of x plus cosine of x plus 1 should equal 0. But I like having my lead coefficients positive, so I'm just going to divide everything by negative 1. And I do that because I know that if I divide the 0 by a negative 1, doesn't matter. It still stays the same. Now I have it here. And I can go ahead and do my factoring. Typically, you guys will do U substitution, but if you guys do enough factoring, you can kind of skip that step, like I'm doing right here. So I need a negative 1 here, I need a positive 1 there, because if I multiply that out, it should work out. So then you have 2 cosine of x plus 1 is equal to 0, and cosine of x minus 1 is equal to 0. X should equal, back it up. Cosine of x should equal 1/2, a negative 1/2. And cosine of x should equal a positive 1. And then using my knowledge of the good old unit circle, very easily I can solve this saying x should equal 4 pi over 3 plus 2n pi. X should equal 2 pi over 3 because it should be in the second and third quadrant. Right? And if I look at cosine of x is equal to 1, cosine of x is equal to 1 at 0. So x is equal to 0 plus 2n pi. But if it's 0, like, and you add it to something, 0 doesn't change that something. So really my answer is just x equals 2n pi as well. Again, with the caveat that n should be an integer value. So that's pretty much it. However, remember, I squared stuff and things. So because I squared, I need to check for any extraneous solutions. So I'm going way back to the original problem, and I'm testing out my solutions. The original problem was sine of x is equal to sine of x divided by 2. All right. Okay. So I don't have to test. I only have to test the principal angles that I found. And if it works for those, then it should work for all the coterminal angles while I'm at it. So sine of 2 pi over 3 should be the same as sine of 2 pi over 3 divided by 2. Sine of 2 pi over 3 is a radical 3 over 2, positive radical 3 over 2. And if I look at the right side, well, this, if I take 2 pi over 3 and I divide that by 2, I'm taking half of 2 pi over 3. So that's really simplifies down to sine of pi over 3. And sine of pi over 3 is radical 3 over 2. Right? So that angle worked because I got the exact same value on both sides. They're both positive. Okay. So this one checks out, not extraneous. It's all Gucci, if you will. No one says that anymore, Rodriguez. If I replace all of these with a 4 instead, four pi over 3 divided by 2, that means it's sine of 2 pi over 3. Sine of 2 pi over 3 we figured out was a positive number. However, sine of 4 pi over 3 comes out negative. So this is not equal. So this does not count as a solution. Because again, I squared. That's why the values are the same, but the signs are opposites, because I didn't take that into account at the very end. You got to check. And then we have 0 plus 2n pi. So let's just test out 0, because if it works for 0, it should work for everything. And hopefully you find my argument for this really nice and easy. So when you plug a 0 in for x, sine of 0 is 0. Sine of 0 divided by 2 is still sine of 0, which is still 0. So that works. So those are my only two solutions. Be careful with these half angle identities. If you ever square something, check your solutions. Positive, negatives matter. All right. So if you guys are good with that, that's pretty much what I have. If you guys want to stick around and see some of the big brainness I was referring to earlier, keep watching. If not, it's been fun, guys. All right. So at this step is where I noted the big brainness. And here's what I note. 1 minus cosine squared is a difference of squares. And I can factor that real quick in my head. And I'm going to rewrite that as 2 times 1 minus cosine of x times 1 plus cosine of x equals, I'm going to put in parentheses, 1 minus cosine of x. Mathematically speaking, these are equivalent. So if I do that, then I can just move everything to the other side, set it equal to 0. So 1 minus cosine of x times 1 plus cosine of x minus 1 minus cosine of x equals 0. And it's there that I can go ahead and do my factoring because I have two terms at this point. And both of those terms have a common factor. And that common factor is 1 minus cosine of x. So, big brain time, pro gamer move, if you will. Which then, if you combine your like terms, all that stuff, this will get you there. So if you can view that and you can understand why I did that, feel free to try to emulate. If you guys are like, yeah, no, that's not me, then you have your other option. I would say that the more you kind of do this, the more you can pick up on some of these factoring patterns kind of quickly in your head, and you can manipulate them this way. It's a good exercise. And again, once I have that in that factor form, it's just to help me get to that step a little in a different way. Yeah, that was the pro gamer move. Thank you for sticking around. Those of you who did. Just if you did, then you should just answer this for your reflection. Of course.